lecture. This lecture will be recorded. If you have anything that you would like to say and you are not comfortable being recorded, please send me a chat message during the lecture. So we're going to leave Zoom and we're going to head on over to, we're going to head on over to PowerPoint and go through our lesson. Oh man, it's supposed to rain a lot the next couple days, huh? All right, so we're still doing momentum, and this is just a review question from last time. Let's try it. Try it at your seats. See if we'll start off with this review, see how we do, see if we can remember how to solve it. There's a 110-gram ball moving to the right at 4 meters per second, catches up and collides with a 400-gram ball is moving to the right. They're both moving to the right. If it's a perfectly elastic, what is the velocity of the first ball after the collision? So here's how we set it up. .09 or 21.10 meters per second. That doesn't sound right at all. I think my thing went order operations.
Wait, did you do 1.2 or did you do 12? Because it looks like you wrote a 12.
I think I did 12. Thank you. Yeah, I was gonna say that is way too big. What's it come out to be when you do 1.2?
Well, I don't know if I did it right, but I got like a negative 0.392.
Yeah, it should be negative. Would you get 0.392 negative?
392, yeah.
That's what I got.
Like that. Sorry about that. All right, so that's review. Any questions on that? Today, we are learning about inelastic collisions. This is when they are going together by themselves and then they stick together after they collide. Like if you get into a car crash or like a football player that's getting tackled, right? And the tackler's hanging on. Or if you pick somebody up and run with them, essentially, that's an inelastic collision. Now, one thing about inelastic collisions that's vital that we're going to go over is that the internal kinetic energy changes. It is not conserved. So we are going to be solving both for the momentum and the change in kinetic energy. So those are the two things we're going to learn how to do today. So when they collide, right here you can see an object. And remember, kinetic energy is a scalar. So this object would have a kinetic energy, and this would have a kinetic energy. And remember, kinetic energy is equal to 1/2 mv squared. So both these two objects, when they collide, if kinetic energy was conserved, they'd have 2k. But what happens is after they collide, they have no velocity. So if your velocity equals 0, that means your kinetic energy equals 0. So instead of having 2k, right, it's not k plus k, we now have 0k. So before the collision, we had 2k. After the collision, we have 0k, right? So kinetic energy was lost. So in an inelastic collision, kinetic energy can be lost or will be lost in an inelastic collision. Momentum, however, is conserved. So P1 plus P2, they cancel each other out. P1 prime plus P2 prime equals 0 then after the collision. The formula, M1V1 plus M2V2 equals big M times V prime, where big M equals M1 plus M2. And V prime is our velocity after the collision. Our new velocity. Does that make sense? So essentially our equation is M1 V1 naught plus M2 V2 naught equals M1 plus M2 V. You don't want to use the prime. So there's just one final velocity. Does anybody have any questions there? All right, let's give this a try. Train cars are coupled together by being bumped into one another. Suppose two loaded train cars moving towards one another. The first have a mass of 150,000 kilograms and a velocity of 0.3. The second having a 110,000 kilogram and a velocity of negative 0.12. What's their final velocity? So M1 V1 naught M2 V2 naught, and our goal final velocity. M1 V1 naught plus M2 V2 naught equals M1 plus M2 V. V equals 150,000 times 0.3 plus 110,000 times 0.12, negative 0.12, over 150,000 plus 110,000. So the final velocity is 0.122 meters per second in the positive direction. Anybody have any questions on that one? Anybody?
So when you have an inelastic collision, are they sticking together?
Correct.
Okay, so they're always going to be the same velocity in the end?
Yeah, they both have the same velocity because they're combined.
Okay.
Anybody else? All right. So two cars collide at an icy intersection and stick together afterwards. The first car has a mass of 1,200 kilograms and approaching at 8 meters per second due south. The second car has a mass of 850 kilograms and approaching 17 meters per second due west. Calculate the final magnitude and direction of the cars. So we have one car. It's going south. And the second car is going west. They combine into a supercar, and that's going to have to go into the third quadrant, third quadrant. Right? So if this car is 1,200 and it's traveling at 8 meters per second, and this car is 850 kilograms and it's traveling at 17 meters per second, this right here is our final momentum. So P1 naught plus P2 naught equals P. Now notice that this is two-dimensional. Remember from chapter 2 and 3 and 4, we have independence of motion. So you can't just add them together. You can't just take 12 times 8 and 17 times 850 and add them together because it's in 2 dimensions. You have to find Px and Py. Does that make sense? So Px is made up of P1 naught x plus P2 naught x. Well, this is 0. So Px just equals 17 times 850. Which is 14,450 kilogram meter per second. And Py equals P1 naught y plus P2 naught y. That's 0. So Py equals 1,200 times 8, 9,600 kilogram meter per second. So P is made up of its two components. So P squared equals Px squared plus Py squared. P squared equals 14,450 squared plus 9,600 squared. Right, 17,348 meters per second. Are we looking for the final momentum? No, we're looking for the final velocity. So remember, momentum equals mass times velocity. Well, this mass here is big M because the cars are combined. Big M. So V equals 17,348 over 850 plus 1,200. .46 meters per second. And it's a resultant, so we got to find this angle, which is going to be .30. So V equals 8.46 meters per second at an angle in the third quadrant of 33.60 degrees. Boom. That's how it's done. Does anybody have any questions on that problem? I know there's a lot going on there, but it's really not that hard. So essentially you're solving for your X and your Y components, right, over here. And then you're solving for P. And then based on the mass of the entire thing, you can find the velocity.
Yeah, so yeah, 8.4 or 8.5 didn't have any of this, it's just section 6. Do you know where I can find that video? Like for all this?
I'd have to look right after I'm done with the lesson today, Ken.
Okay.
Anybody else have any questions on this problem? All right, let's move it down the line then. All right, so you guys find the first part, and I'll help you with the second part. During an ice show, a 60-kilogram skater leaps in the air and is caught by an initially stationary 75-kilogram skater. What's their final velocity, assuming negligible friction? Give that a try. All right, let's check it out. We got M1 is 60 kilograms. V1 naught is 4 meters per second. M2 is 75 kilograms. V2 naught is 0. And we're looking for our final velocity. So M1 V1 naught plus M2 V2 naught equals m1 plus m2 times v. This is 0. 60 times 4 over 60 plus 75 equals v. V equals 1.78 meters per second. So that's the final velocity of the whole system. Part B says, how much kinetic energy is lost? Well, delta K equals K minus K naught. Sometimes you'll see it written as K prime minus K. Delta K equals 1/2. Now remember, this second K here is M1 plus M2 V squared. That's the big M. Minus 1/2 M1 V1 naught squared. Plus 1/2 M2 V2 naught squared. It's a good thing that's 0 because I ran out of room. That's 0. Delta K equals 1/2 times 60 plus 75 times 1.78 squared minus 1/2 60 times 4 squared. We lost 266.13 joules of energy. Any questions on that? Anybody? All right, next one. Now, this is a big one, so I'm going to use 2 slides for it. But we're getting pretty near the end. This lecture is fairly short. A battleship that is 6 times 10 to the 7th and originally at rest fires a 110 kilogram artillery shell horizontally with a velocity of 575 meters per second. If the shell is fired straight aft towards the rear of the ship, there'll be negligible friction opposing the ship's recoil. Calculates recoil velocity. And then part B, calculate the increase in kinetic energy for the ship and the shell. So what this is saying is that before it's launched, the initial kinetic energy is 0. Then after it's launched, the ship and the shell have a kinetic energy. So this time, your initial kinetic energy will be 0. So you guys give this a try, this whole thing at your seats. How we doing? Can we go to the first part? Make sure you got it right before we go to the second part. So M1 is 6 times 10 to the 7th kilograms. V1 naught is 0. M2 is 110 kilograms. V2 naught is 575 meters per second. Sorry, that is just not what this is what we're solving for here, essentially. Kind of blanked my brain. This is an opposite problem. V1 naught is 0. So in this problem, 2 become 1, right? 2 become individuals. So the momentum before is 0, and the momentums after are equal to a value. So here we have big M V naught equals M1 V1 plus M2 V2. Because before they're fired, neither one of them have a velocity. So 0 equals 6 times 10 to the 7th V1 plus 1100 times negative 575. V1 is going to be relatively small. .01 meters per second, 0.11. So it's barely moving. How'd we do on that?
Yeah, that's what I got. I just kind of did it in a different way.
Okay, well, that's good that you got that value. Now we're going to take this value and do part B. So try part B. I'll give you a minute to figure that one out too.
I think I got the answer.
Okay, is everybody ready? Just kind of chilling, waiting for everybody to get done here.
Yeah, I'm a little stuck. So
All right, so in this problem, we are trying to find kinetic energy afterwards. So let's just take over what we know. We know V1, we solved that to be 0. What was it? 0.011. Is that right? Meters per second. So delta K equal, oh, what happened there? K minus K naught. Well, we know the initial velocity is 0, so delta K is just going to equal the K gain. So that's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So delta K equals 1/2 times 6 times 10 to the 7th times 0.11 squared plus 1/2 times 1,100 times 575 squared. It's a big number, isn't it? A lot of kinetic energy gained when that missile is fired.
Well, it's a shell, not a missile.
Shell, sorry. Be less if a missile was fired, I think. Who knows? I don't know. Do you have any questions there? Anybody?
Works for me.
Works for you. Nice. All right, I think the quiz is upcoming. All right, quiz time. Give you a minute, then I'll go over to Moodle. Everybody have that copy down? I can head over.
Yeah, I'm good.
Yep.